Hello, I am Owen V. Murray, and I have done my presentation on the quasar light curve analysis done by the SDSS-RM Reverberation Mapping Multi-Year Survey. Quasars are large, actively feeding supermassive or ultramassive black holes in the centers of faraway galaxies. Quasar light curve variability within the accretion disk and the broadline region shortly outside the accretion disk is measured with the Sloan Digital Sky Survey, or SDSS, Reverberation Mapping Project. The key emission lines that we focus on are the H beta emission line, which is the main focus of this project. Other emission lines not studied were the MG2 and C4 emission lines. This project looked for normal and abnormal variations and variabilities within the reverberating AGNs, active galactic nuclei, and quasars. Reverberation mapping is a technique for measuring the fluctuations in emission and continuum light curves between the two regions of the nucleus of a quasar, which is the accretion disk, which is what is immediately surrounding the black hole and being actively sucked into the black hole, and the broadline region, which is immediately outside the accretion disk. The SDSS campaign does multi-year data collection for 850 target quasars, and they gather spectroscopic and photometric data for the reverberation mapping study over the course of several years from 2014 to the current day. This is an illustration of what exactly reverberation mapping does, as the energy emitted from the accretion disk is shot outwards. It bounces off the cold disk of the broadline region and is then re-emitted towards the observer with a time delay of several days to up to a year, depending on the size of the accretion disk and the broadline region. Light curves are changes in the mean luminosity and the spectroscopic content of the accretion disk and broadline region. The fluctuations in emission lines of the accretion disk and broadline region are measured and tracked over 6 months periods every year. The time lag compensation of the emission is what determines the size of the accretion disk, as larger accretion disks have a longer time lag as light takes longer time to travel from the inner part of the disk to the broadline region. In this project, we were researching as of what constitutes as abnormal variability in a quasar light curve, and what percentage of these variable quasars are hypervariable, and how many are non-reverberating at all. Also, why do these abnormal variations occur, and what is the difference between a short and long-term observations and how does that show what is going on with these nuclei of these quasars? Well, there is not really any such thing as a perfect example in the real world. This example, this target called RM518, is the closest that I found to an ideal reverberation mapping target. The time lag lines up very nicely, as seen in the very bottom panel, and there is a very nice, clear, both short and long-term pattern between the H beta curve, seen second from the bottom, and the overall continuum curve, seen second from the top. It is very easy to track the patterns and what is going on in both of these curves and see that they line up and correlate very well. And as this target only has a time lag of 39 days, this is a relatively small target, which helps as it is much more able to change within a human timescale as the much larger targets, where the time lag is over a year. Some targets, however, don't reverberate, and this one, RM90, is one of those examples. As you can see, there's not really any pattern to either the H beta or continuum light curves, and they don't really line up, which indicates that there's not really any reverberation going on between the broadline region and the accretion disk of this particular quasar. So that is very interesting because of the lack of the expected activity. And then the most interesting target that I had found was RM121. There is a very large and distinct fluctuation and a very periodic that in both the accretion disk and the broadline region that potentially indicates the influence of an orbiting object within the accretion disk or between the disk and the broadline region. This could potentially lead to a discovery of a new star or even a clump of cold gas within the disk itself, which would be very interesting as it shows that an external object has a measurable and predictable outcome and impact on the reverberation of a quasar's accretion disk and broadline region, which, if confirmed, would help detect more of these objects in the future. Other noteworthy examples that I had found were RM440 in the top left, such as which had a very muted reverberation as the accretion disk had a very variable. And while the H beta did follow, it did reverberate, something was making the disk not follow through as well as the broadline region. In RM017 at the top right, there was a very large spike in energy that showed that this quasar, which started out as a very low energy target, over the course of 3 years became a very high energy target. RM078 indicates a pulsating disk, where the disk itself changes size over time as the temporal lag starts out at around 100 days and ends up at around 84 days as the size of the disk changes. And RM192 has almost no H beta variation whatsoever, indicating a similar impact to RM440, just more pronounced. An overview of the results: I analyzed 181 targets in this project and found 68 of those targets to be noteworthy. 58 of those targets showed abnormal behavior, and 10 were highly abnormal. For future research, we should consider the questions of, are there different subclassifications of these variable quasars based on their variability? And do all variable quasars go through a hypervariable phase or a non-reverberating phase? And do quasars go through periods where they stop reverberating? If so, how and why do they start reverberating again? To answer these questions, we need to have continued multi-year long-term observation of all these notable targets with the SDSS and various other telescopes and observatories, and to observe these targets in other wavelengths and spectra to determine the extent of the variability of these quasars in a larger, more thorough data set. In conclusion, this is a very new area of research that definitely needs to be studied further, because quasars are very important to understanding the early universe and how galaxies evolved.